Hello, everyone. So thanks to the previous two talks who have already introduced galaxy clusters and the non-thermal emission components in them. So I'll be giving an overview of the work that we are doing. Thank you. Yeah, so galaxy clusters, as you heard, are the largest gravitationally bound structures in the universe. To draw your attention to the components that I'm interested in, so galaxy cluster mass is mostly dark matter, and of the 10 to 15% baryonic mass, most of this baryonic mass is in the diffuse medium, the intracluster medium, and that is the topic of our interest. So this, again, this intracluster medium is mainly thermal plasma, which you see emitting in X-rays via the thermal Bremsstrahlung. However, there are these elusive components of the ICM, magnetic fields and relativistic electrons, which show up as radio emission. So we are interested in diffuse radio sources that are not associated with individual galaxies. They are associated with the large-scale intracluster medium itself. And they are the two broad categories, radio halos and relics, that we just heard about. So radio halos are centrally located in clusters. Relics are located at the peripheries and are arc-like. In this image, you are seeing Abel 521, which is a system containing a radio halo and a system of double radio relics. And here you are seeing Abel 3376, which is a merging system having two double radio relics. So these are typically steep spectrum spectral index sources, typically steeper than -1.2. And they are tracers of relativistic electrons and magnetic fields in galaxy clusters. So these components allow us to probe the physics related to this plasma. So this plasma is characterized by high beta, and it is weakly collisional. And there are these plasma processes in this high beta ICM: shocks, turbulence, magnetic fields, and particle acceleration. These are the things that we can access via radio studies of galaxy clusters. So the radio sources in galaxy clusters can originate, of course, from galaxies, the known AGNs, or galaxy feedback. In addition, there's energy put into the intracluster medium because of the mergers of galaxy clusters, and this is dissipated in the intracluster medium, and all of this chain of processes leads us to radio emission in certain conditions. So this AGN feedback is a more familiar phenomenon, where you have a radio galaxy at the center, and there's this blue X-ray emission, and it puts out jets and makes cavities and plays a role in heating the ICM. What we are interested in are these diffuse components on megaparsec scales, which are called radio halos, and they are originated. They originate or they get generated because of the relativistic electrons, which are accelerated through processes involving turbulence and shocks. There are also cosmic ray protons associated with the hadronic collisions are gamma rays, which as yet are undetected or marginally detected only in one case. So radio relics are related to shocks, tracers of shocks, and that's what we are trying to probe. So there are several open questions. They were mentioned in previous talks, but how do these electrons get accelerated? What is the role of cluster mergers? How much energy do they put in? How much goes into the non-thermal components? And what are the properties of these radio halos and relics across redshifts? This will allow us to probe the properties of the magnetic fields across redshifts and the acceleration processes. So why would it interest cosmologists? Just to address that, okay, these are radio continuum sources, and they're also forming a part of the foregrounds that matter to 21 centimeter cosmology. I've seen this being taken note of, and there is this paper I found estimating contribution of radio halos to EOR foregrounds, but experts can point me to rest of the literature, which I may not be aware of. So our work focuses on the work that I'm presenting here is basically a survey. So surveys and individual systems of interest. And I'll also touch upon superclusters. So Southern Cluster Scale Extended Survey is a survey of galaxy clusters selected from the Planck satellite and the South Pole telescope catalogs. These are basically massive clusters at low redshift and selected specifically in the southern sky, where there were basically the surveys had so far missed these systems. So we have a sample of 20 clusters which we have undertaken a study of, and they span a redshift of 0.07 to 0.28. So we have so far surveyed 9 clusters with the GMRT, the legacy GMRT at that time, and 5 of these were also covered in the MGCLS, the Meerkat Galaxy Cluster Legacy Survey, which Kenda talked about. So we use data which they have made public, and we have results of several detections. We also came up with a detection which was a very interesting system because it formed a transition system between a radio halo, which is typically in a merging cluster. This resides around a brightest cluster galaxy, and it's a transitioning system between a mini halo, which is typically around the central galaxy in relaxed clusters. So there is a poster you may have come across by Pralay. Coming to radio halos, there is an ultra steep spectrum, the prototype ultra steep spectrum radio halo, which was discovered back in 2008 using the GMRT. So these systems are of interest because they challenge the models of acceleration. We made deep UGMRT and used the MGCLS Meerkat data to make very detailed maps of this cluster, which contains the ultra steep spectrum radio halo. So this is a band 3 map, 400 megahertz, which shows the radio relic, the radio halo, and also a second relic over here. So we could go quite into details of this study, making a spectral index map between the band 4 and band 3 observations that we had. We also pointed out that there is an extension of the relic, which is almost as long as the existing size of the relic, which as yet we don't know what basically causes this extension over here, which is somewhat offset from the X-ray emission, which is mainly over here. And we also could do scaling relations between the radio surface brightness and the X-ray surface brightness. These scaling relations basically can allow you to distinguish between the models which for reacceleration, in various different conditions. So in this work, there was RFI filtering, the real-time RFI filtering mentioned earlier on the first day in Nityanandan's talk. So in this paper, we have an appendix which shows how the real-time RFI filtering affects imaging and how it allows you to use the central square baselines of the GMRT more effectively for studying the diffuse emission. There is another work which I want to point out on the cluster Planck G171. This focused on a candidate ultra-steep spectrum radio halo discovered back in 2013. But we found with these better sensitivities observations with UGMRT and JVLA that it is actually not an ultra-steep spectrum radio halo. There were also some things interesting about the scaling relations that came up in this work. So I'm talking about galaxy clusters, but of course non-thermal components or magnetic fields and cosmic rays are not confined only to these systems. There are also galaxy groups where we are interested, and Ramananda, who has done these works, will be talking about the group systems tomorrow. Coming to low mass clusters, considering the non-thermal components in galaxy clusters, earlier studies, of course, detected the brightest radio halos, and they were mainly residing in massive merging clusters. But with better sensitivities in the past decade, one has gone much deeper and probed low mass systems. And what has become clear is that maybe merging systems in lower mass clusters as well are capable of producing shocks that can lead to radio emission of relics relic kind. So in 2017, we had discovered a radio relic in this particular cluster, which we used Meerkat and UGMRT and our deep Chandra observations. And we've come up with the geometry of model propositions for the geometry of this merger. And thanks to Meerkat data and UGMRT data, we have detections of multiple relics in this system. So it has become like from a low mass single relic system, it has gone on to become a multiple relic system and a complicated merger. We also pointed out something interesting about the spectral indices of radio relics in low mass versus high mass clusters. We found some difference in these. So that is also something interesting that we found in the pursuit of this low mass cluster. So now talking about high redshifts. As Kenda also mentioned, it is only recently that we are talking about high redshift clusters with radio halos, because we've reached those sensitivities where we started to detect. But the main reason why they were not detected earlier, because and they were also the understanding was that maybe there won't be as many halos at high redshift because of the inverse Compton losses. So as you go to high redshifts, you will be basically, the relativistic electrons will be losing energy to the inverse Compton because of the photons of the CMB. And therefore, what one would expect that at high redshift, there may be radio halos, but maybe they are rare, and maybe they are steep spectrum. So now observations are capable of confirming or allowing us to investigate this. And also a curiosity is that at what redshift do we expect enough mass assembly to produce radio halos? Because we need magnetic fields to reach the levels where you would expect detectable synchrotron emission. So protoclusters are also of interest, but I'm not going to touch upon those. So this is the picture as one would say not so long ago, but it has evolved very rapidly. In 2012, this is the histogram showing the radio halos across redshifts. You can see the numbers are really, like there are, I would say, less than 10 in any redshift, given redshift bin. So two reasons. One is that the sensitive surveys was at that time had not reached those sensitivities where you would start to detect. And then basically, this got basically addressed when there were pointed radio surveys, for example, the extended GMRT radio halo survey. So we surveyed clusters in the redshift range of 0.2 to 0.4 systematically, and then the statistics basically grew. At one point, there was in 2014, once the Planck and SPD and ACT catalogs came online with the detections of massive clusters at higher redshifts, at 0.87 redshift, there was a discovery of radio halos and halo and relic in El Gordo. So we followed this up with the upgraded GMRT. This is the most massive cluster at high redshift, like greater than 0.6. It's a massive and hot cluster. This was the discovery by Lindner et al. In 2014 using the ATCA and the GMRT. This was the legacy GMRT. They also detected polarization from the northwest relics. We also did X-ray study back in 2016 where the radio relic was basically studied in more detail, where we found that we could even explain it using diffusive shock acceleration operating on thermal electrons. We carried out UGMRT observations, thanks to the MGCLS. There is also very deep Meerkat observations available. So this is the radio halo and the two relics, and even an extension of the relic that we found. So this X-ray emission in Elgato is characterized by two tails, the northern and southern tail. And we find that there is a difference in the radio emission characteristics along these two tails. We made deep images at all the three bands and got detailed spectral, spectral indices for these components. So one interesting thing I want to point out is that there is likely a steepening in the spectrum of the radio halo at frequencies higher than 1.2 gigahertz. And this implies a maximum acceleration time of about 41 mega years as compared to 400 mega years for coma. So you can see as you go from the nearby coma cluster to the 0.87 redshift Elgato, the time that you have for accelerating the relativistic electrons is getting very short. And therefore, you need to think about how would you efficiently accelerate. So something must be keeping up the acceleration efficient in order to have this bright radio halo. Coming back to statistics where Elgato stands today, it's not a unique high redshift radio halo anymore. We have many more detections. So I'm showing this 1.4 gigahertz power versus mass, and Elgato is plotted as stars along with the nearby as well as high redshift samples that we have today. So it still is a among the brightest radio halo, but there are a number of new radio halos that have been detected at higher redshift. So basically, this is an interesting case. We also carried out spectral index mapping of this radio emission, where we found the resolution is still limited in the spectral index map. So really going deep with instruments like SKA would help us to have much more resolution in order to go down to really the scales at which the reacceleration mechanisms can be basically looked at. We also did the scaling relations. There were deep X-ray observations available. We also made a density fluctuation analysis using the X-ray image. And we found basically this analysis allowed us to compare and make some predictions that can be verified with the X-RISM-like instruments. So Elgato is a very interesting system. We have MeerKAT 1.28 gigahertz already, and we would like to do polarization study to understand the depolarization towards the northwestern relic and also MeerKAT UHF. It is an important target, I would say, for the SKA because it is very favorably located at a declination of minus 49 degrees. And we would like to, so in this study, what we have done so far, we have used our data analysis pipeline capture CASA 6 and also online RFI filtering. There's a new pipeline coming up, and Arpan, who is also at this meeting, will be talking about it. So the picture today, evolving from this 2012 picture, we have many more radio halos now in this redshift bin. So all the way you can see the redshift axis now goes all the way to 1.4 or so. So beyond radio halos, now we have also detected emission which goes and it's much more extended. So the extent at over which the cosmic ray electrons can get accelerated is basically our understanding about that is evolving. So there are something called mega halos that were discovered in 2022 using LOFAR HBA or 144 megahertz. Also, there was a deep field study towards ABLE 2255, I think about 75 hours on this cluster with LOFAR, and they also detected diffuse emission much beyond the known radio halo extent. So I would like to point out this work which we did recently. Samir Sarunkhe, who did this work, is also at this meeting and will be talking about superclusters in his talk. But this is a mega halo discovered in this Planck 287 using the GMRT at 400 and 650 megahertz observations. The profile, the surface brightness profile also conforms to some of the profiles that were found for the LOFAR mega halos. This is the highest frequency detection so far of a mega halo. So coming to superclusters, Superclusters are largest, one would say, loosely gravitationally bound structures in the universe. So Shapley is a well-known supercluster at a redshift of 0.04. Saraswati supercluster was discovered in 2017 by Jaideep Bakhchi's group, and it is a supercluster which has similar characteristics to Shapley, but is located at 0.28 redshift. So we have undertaken a project to study whether we can find some evolution between superclusters at 0.28 to 0.04. So there is, we know a little about magnetism in the diffuse medium in the superclusters. There are simulations which have put out, and there are statistical studies which have also come up with estimates of the order of magnitude of the magnetic field that is expected in the superclusters. So one aim is to, of course, detect something beyond the cluster scales and on supercluster scales, but that is in the era of SKA, sorry, SKA sensitivity. What we have undertaken right now is with the UGMRT and Meerkat. Excuse me. So Samir will be talking about it. I won't dwell on it too much. But at the end, yeah, sorry, thanks. Towards the end, I want to point out that the GMRT sky, sorry, 1 second. So GMRT has a large overlap with the SKA sky, and right now it is basically, it also has a very large overlap with the LOFA sky. It is a favored instrument for follow-ups with LOFA discoveries or the Meerkat discoveries, and will continue also in the SKA era. And these are the clusters from the SZ samples, which would be accessible to the SKA in the southern hemisphere and the LOFAR in the northern hemisphere. So with that, I want to summarize that non-thermal emission on galaxy cluster scales has, basically our understanding has evolved rapidly over the last decade, thanks to the SK pathfinders like the UGMRT and precursors like LOFAR and Meerkat. They're contributors to the foreground, so maybe they matter to a much wider community than just the galaxy cluster community. Wide surveys and deep observations of individual clusters are crucial to understand the plasma physics, like the acceleration mechanisms, the role of mergers, and magnetic field amplification. We have studied this high redshift cluster Elgato, which is also among the brightest systems, and it is a very promising target for the SKA. And on superclusters, there are new avenues to study the evolution of AGN and radio galaxies by comparing Saraswati to the Shapley supercluster. And we are working right now with the pathfinders and precursors, which are testbeds for our data analysis techniques and science. So techniques like these real-time RFI filtering, improving upon the data handling and efficiency of our data analysis pipelines also matters for this study. With that, I will stop. Thank you.
Thanks, Ruta, for a very nice talk. We have time for questions.
Was that first?
Please go first.
Okay. Yeah, thank you for the very nice overview on all these exciting results. Do you have any concerning the superclusters? Do you know any simulations which give the cluster merger rate in superclusters, so that we have an expectation? So how many more merging clusters do we expect in superclusters compared to field regions?
Yeah, nothing comes to my mind right now from the existing literature, but it would be interesting to look at in the new simulations, maybe like TNG or others. I don't have an answer for that, but it's an interesting.
I think even old, but it must be a large volume dark matter simulation from the merger trees. One should know what is the merger rate in superclusters.
Yeah, possibly that number may be buried in the literature. I haven't come across it in.
Thank you.
Right.
Hi. So in one of the slides, you mentioned that the spectral index is different than in like low mass clusters and high mass clusters, where you have shown in 2 histograms. I mean, what could be the reason for this?
Yeah, so yeah, let me go back to that slide just quickly to show you the value. I think it was the yeah, this one, right?
Yeah.
So you can see this blue are the low mass clusters and red are high mass clusters. So
Right.
this basically our intention was to see whether high mass clusters produce more like higher Mach number shocks, and is that the reason behind uh, uh, this split basically? That could be a reason because spectral index is essentially, if you look at the Mach number here basically, it's a proxy for Mach number. So that is the simplest explanation I can give. But as yet, I wouldn't say this is very statistically robust as yet because the samples are small and then the separation is not very significant, I would say.
I see. Thanks.
Thank you, Ruta, for the nice talk. I wanted to ask whether these mega halos, you showed a low-far image, are these very unique, or if we did also, very low frequency observations of more clusters, it would be common?
That's a possibility, yes, because the mega halos are all basically the ones discovered with the LOFAR are essentially extensions of radio halos, meaning a larger envelope surrounding these radio halos. So if we look at the radio halos that we know of with similar sensitivities, we are likely to see many more. And LOFAR, low band array, LBA LOFAR, that is only now starting to produce sensitive images, and those that would likely pick up the mega halos.
So clusters like Coma and Virgo, will we see mega halos, you think?
Yeah, they are. One thing is that Coma is too nearby, so you really need essentially single day shot, you need very short baselines to map structures which would be of the order of 1.5 degree or something, maybe up to a degree in size for Coma cluster. So it would be difficult, I would say, in clusters as close as Coma, but maybe 0.1, 0.2 redshifts would be more in that zone where you will find detection.
Thank you.
I have a quick related question that the histogram that you showed about the number of detections, there are about 10 mega halo mark there. Is that correct?
Not the mega halos. Sorry, which?
This MHS are what? That, sorry, maybe.
No, these are all radio halos. The statistics or the histograms that I showed were all for radio halos, not for the. So mega halos are just right now only a few. So there were 4 which LOFAR discovery paper showed, and there's one more that we have put out. At least, I don't know, unless there is a paper last week or something. I'm not aware of more.
Any more questions? Okay, so no more questions. So let's thank all the speakers of the morning, also for keeping excellent time.